So last time we defined the creation and destruction operators in real space, and they are related to the creation and destruction operators in momentum space by a Fourier transformation, and the transformation is based on this kind of a Fourier theorem that you can always rewrite the Schrödinger wave functions in terms of orthonormal basis of any other wave functions in other eigenbases. For example, this K represents the eigenbasis for momentum operator. So you can rewrite the Schrödinger wave function in terms of a linear combination of this wave functions in momentum space. And you can second quantize this kind of a Fourier decomposition by using this kind of Dirac notation that you could insert this empty state zero vacuum anywhere you like, and you use Dirac, Broglie, Castet representation of the Schrödinger wave function, and therefore you could re-express this linear combination or Fourier decomposition in terms of second quantized fields. And in this case, if I create a fermion in real space R, and it is rewritten in terms of the linear superposition of a creation operator A dagger K in K space with the coefficient. And this coefficient, if you translate this coefficient in terms of a first quantization or Schrödinger representation, it is nothing but the Schrödinger wave function for, say, a free electron, which is a plane wave, e to the ik dot r. So we will see that in just a moment. So likewise, we could destroy, say, a fermion in real space R, and this destruction operator in real space is related to the destruction operator in K space by this Fourier decomposition theorem. All right? Okay, so this is nothing but what you already learned in quantum mechanics, which is a Fourier theorem, but in the second quantized form. So you can verify, and in fact, it was your homework problem, right? Assigned to you last time that you could verify that the fermion operators psi and psi dagger satisfy the standard commutation rules in real space. Okay, suppose the similar anti-commutation rules in K space is satisfied. Okay, suppose we have such anti-commutation rules for Fermi operators in momentum space AK and AK dagger prime, and so the anti-commutator of these two operators gives you this Kronecker delta function, delta kk prime, which is either 0 or 1. But if you Fourier transform this to the real space operators, and they satisfy the similar but slightly different form of the delta function, which is the Dirac delta function. And the difference between the Dirac delta function and Kronecker delta function is that this Dirac delta function gives you infinity when this argument inside the bracket vanishes, but the peak of this delta is infinitesimal narrow, so that you get almost vanishing peak width, but almost infinity peak height. So the integral over such an area of delta peak is still 1. Okay, so that's from your applied mass. So now we could just interpret this, the other eigenbasis K, literally the momentum eigenbasis. Okay, so this is nothing but a Fourier transform of your quantum mechanical operator or Schrödinger wave functions in between the real space and K space. Okay, but in general, this K does not necessarily to be the momentum operator. The eigenbasis for momentum operator. This K could be any other eigenbasis. Okay, so as long as this is the complete set of eigenbasis, and that's fine. For example, this angular momentum eigenbasis. right? Or other, eigenbases for certain, say, simple systems such as the principal quantum number in a hydrogen atom, or whatever quantum numbers that labels the quantum states. Good, okay, and therefore this coefficient here, psi star k of r, is nothing but e to the minus I k to r in this case, and we could officially just study the Fourier transform of a quantum field operators. Okay, so let's just take this Fourier transformation as our starting point, and we know that we can define this destruction operators in real space and also in momentum space. Okay, like this. So that we can rewrite our kinetic energy and potential energy of this free electron gas problem. So previously it was written in terms of the momentum variables, right? This form was derived earlier, right? So we could just second quantize the electron operators, in terms of its momentum variables, and we sum over, all such momentum space. Of course, we need to sum over the spin, but could actually forget about the spin indices at the moment. Just focus on the Fourier transformation between the real space and k-space variables. And this kinetic energy for free electron term could be rewritten in terms of the creation destruction operators in real space. Okay, so by Fourier transformations, then you could apply such inverse Fourier transformations, which takes from this k-space to real space. Right? So there are double Fourier integrals when you simply just plug in this inverse Fourier transformations, taking you from ck to psi r and c dagger k to psi dagger of r. And these two Fourier integrals are performed independently. Okay, so you get the two independent Fourier coefficients, e to the plus minus I k dot r, r1 or r2. And for this, dagger term, you get a minus sign because of a complex conjugation of this e to the I k r. So that's it. Performed this Fourier integral by looking at just the stuff inside this orange circle, which is this delta function, the Dirac delta function. If I sum over all these momentum variables, e to the I k dot r, and it gives me delta of r. Okay, so we have proved that, and you should have proved that sometime when you study this applied maths or quantum mechanics. Good. So we could take advantage of such a Dirac delta function and plug in here, and we could get rid of one of the double integral over r. So I get rid of dr1. So by using this delta function, and therefore integral over dr is gone. So I can relabel this vector r as I like. So I could rename this, say, dr2 as just dr. And therefore these two operators, psi dagger of r1 and psi of r2, are at the same real space vector r. So these position vectors appearing in these two operators is the same, right? Good. And some of you should recognize this form. Okay, so what is this? What is this? Okay, so if you learn a little bit quantum mechanics, you must recognize this term. So what is this? Well, it looks like a kinetic energy for the Schrödinger wave function, right? If you have a single particle in Schrödinger picture, and this is the kinetic energy of a Schrödinger particle, right? It looks like, except this is not a Schrödinger wave function, but operator, right? So they are wearing a hat representing this is the second quantized fields, but the mathematical formulation bears striking similarities to this kinetic energy of quantum particle in the Schrödinger picture, right? So now let's just officially link this formulation to the Schrödinger wave function that you are familiar with in quantum mechanics. So this is very important. This allows you to really think of this quantum particles either in the Schrödinger picture or in the second quantized representation, and this is the key. So let us just show this link. I write it here. So the link between the first and the second quantization is the following. It's very simple. It's just a Dirac notation, nothing more. Okay. So the only trick that we played here is just the Dirac notation, and we just relabeled this Dirac notation in terms of creation and destruction operators, and nothing more. So let's just start from this second quantized form for a kinetic energy of a free, say, electron. Okay, so remember, destruction operator in real space and k-space are defined in this fashion, that we first destroy the single particle state either in real space or in momentum space, and then create an empty state, right? Okay, so let's just plug in such a definition. And this K in this second quantized representation stands for an operator, a quantum mechanical operator. Okay, so let's just take a excitation value of this operator K, and I sandwich this by the eigenbasis in real space, say vector R. So if I do so this is simply just a form of this excitation value of a operator. But if I do so, then you will immediately recognize the link between the Schrödinger representation and the second quantized representation. Okay, so now let's just look at the definition of the Schrödinger wave function, but in terms of the Dirac notation. So everyone should remember this definition, which links the Dirac representation of a quantum state and the Schrödinger wave functions in real space. Okay, so in other words, if I write the quantum states in the Dirac notation, it could be either a Broglie cascade. In this example, this psi state is a Dirac cascade. Okay, but the specific form of such a Dirac state is arbitrary. Okay, unless we project this Dirac cascade onto any specific eigenbasis. If I project this psi, some quantum states, onto real space eigenbasis R, then this is precisely the definition of a Schrödinger wave function, isn't that? Okay, it represents the probability distribution of a single quantum mechanical operator, the quantum particles in real space. Okay, so this tells you, so if I plot the magnitude square of this Schrödinger wave function in real space, this tells you the probability of density of finding such a quantum particle in real space. And this is, the definition of a Schrödinger wave function, psi of R, but you need to recognize the Dirac representation of the Schrödinger wave function is the Dirac cascade or Broglie projected onto a specific eigenbasis. If you study this, the wave functions in real space, and that basis should be the real space. basis, and this R is the Dirac state, is the eigenbasis of this position operator. You know, this position operator, when you're acting on this position eigenbasis, you see this position as an eigenvalue multiplied by this Dirac cascade of a position eigenstate, right? So I need to understand this, and I reviewed this transformations in a much deeper way. Okay, so you need to understand that the Schrödinger wave function is nothing but a special case of a quantum mechanical states projected onto the real space. If you project the quantum state onto different eigenbases, you get different wave function, which is different from the Schrödinger wave function. For example, you must remember this, right? Again, so if you have this Dirac cascade phi, but instead of projecting this phi state onto the real space, I project this phi onto this momentum eigenbasis, and the resulting quantity is not the Schrödinger wave function, but the wave function is momentum space. Remember that. This is the wave function in K space. So we call this Schrödinger wave functions, but officially we should call this as a wave function or probability distribution of a quantum particle in real space. Right? So the relationship between the Schrödinger wave function in real space and this wave function's momentum space is a Fourier transformation. It's precisely the Fourier transformation that I've written here that goes back and forth between the real space wave functions and momentum space wave function. Okay, so this is nothing more than this Fourier transformation that you already learned. Okay, so now it's just we put it in the fancy notation in the second quantized form, but there's no second quantization, strictly speaking. We have only the first quantization, which is the, say, Schrödinger picture or Dirac notation, but we can rewrite everything in terms of the second quantized fields. So that's the trick. Good. So now you understand this, so we can plug in this kind of projected Dirac states onto the Schrödinger wave function, and we get exactly what we know. So if you look at this, what this is R and psi of dagger. What is this? Psi and 0 and 0. Agree? You plug in definition of psi dagger, in terms of that yellow box over there, and you get this stuff. So this is your psi dagger, right? So there's a state in Dirac notation, a Dirac cascade psi of R, and you first destroy the empty state and you create a single particle state in position R, and this is psi dagger of R as a second quantized fields. So now once you write down the definition of this psi dagger, you forget about this red circle and you look at the new red circles. Okay, so this projection of this 0, 0 states is actually normalized to 1. Okay, so you forget about this. This is 1. What this is? This is precisely the Schrödinger wave function, isn't that? Right? So this is psi star. So now it's not dagger, but star. Star represents the complex conjugate of that function. So this psi star is not the operator anymore. It is the Schrödinger wave function. It is a function. It's not the operator. And then this is simply copy. And of course, you know this is a sub R on the right. Okay, so what this is nothing but the expression value of your kinetic energy in the Schrödinger picture, isn't that? Okay, sounds like a magic. But let me tell you, this is not a magic. This is just a rewriting this, say, Schrödinger wave function in terms of a second quantized fields that we can count the particle number. So in the Schrödinger picture, we don't count the particle number because we don't have such an operator which allows us to destroy or create a particle. We just know their wave function. That's all. Okay? But we could rewrite this Schrödinger picture of a kinetic energy in terms of the expression value of a kinetic energy operator, k wearing a hat. So now, if this k wears a hat, then we can really count them, because this is a quantum mechanical operator. Okay, in the second quantized form, where we could either destroy the particle in momentum space, or we could destroy the particle in real space. Okay, so this is part of the review of your, say, quantum mechanics. But then it's more than the review of a quantum mechanics, but we go beyond this Schrödinger representation of a quantum system, and we take advantage of a Dirac notation, and we rewrite everything in terms of the second quantized fields. But of course, the mathematical format still resembles the first quantization in Schrödinger picture, except now you should interpret this psi diagram psi not a Schrödinger wave function, but the creation destruction operator in real space. But they are closely related to the Schrödinger wave functions. Okay? So in other words, this kind of operator, a second quantized operator, representation of a quantum system, is not coming out of nothing. So these formulations is built or is based on the quantum mechanics that we know. So there's no magic, no mystery, no nothing. It's just re-expression of your quantum mechanics. So I believe that you should be able to understand this relation between the Schrödinger picture and the second quantized form. Good. So let's take a short break, and we'll come back. We will continue using this second quantized fields to calculate something, namely the value of the average kinetic energy and also the potential energy. And let's just take a short break. So now things become more interesting, and you have more fun. So now we are able to count the particle numbers, and we will count. So speaking of this counting the particle number, so this is your homework, new homeworks. So we know this number operator for, say, electrons, electron destruction operator. And we know that there's anti-commutation rules, right? So now you need to prove there's a commutation relations and this. So the anti-commutation rules are satisfied by a single creation destruction operator, C nu and C nu dagger, like this. But there are commutation relations between the number operator of a fermion operator and a single destruction and creation operator of a fermion. So we will take advantage of such relations later. Okay, but first it's very easy to prove this, because you can simply use this anti-commutation rule for fermions, and you could derive this very easily. So let me define the commutator. So this is a standard definition in quantum mechanics. If you calculate the commutator between two operators A and B, and this is defined as AB minus VA. Remember, this is not zero in general, because these A and B are operators, so they may not commute. If they don't commute, and which is usually the case, then this difference is non-zero. So let's try to evaluate the kinetic energy and potential energy of an almost free electron gas. But this is nothing but a review, again, of your solid state 1. So first of all, let's derive the potential energy of a coolly interacting electron gas. So say the Hamiltonian of this coolly interacting electron gas is the free electron kinetic energy and plus the Coulomb term between a pair of electrons. Okay, so this is the usual term that we have written down many times, but this Coulomb term, we only derive the real space, right? Representation of the Coulomb interaction term. So let me refresh your memory. So remember, two particle interactions take this form, right? So this alpha, beta, gamma, delta is just labels for initial and final states. So you have two initial states, gamma and delta, and if they are electrons, they interact by Coulomb, and then later they become new two electrons carrying quantum number alpha and beta. Okay, so this is your general form for two electron interactions. Okay, so now we could realize this: the states alpha, beta, and gamma, delta are both in real space and in K space. So you could imagine that this alpha, beta, gamma, and delta could be in momentum space. And the reason why we like to represent this Coulomb interaction operator in K space is because we know that for nearly free electrons, we have a Fermi surface, right? And as I mentioned this many times, that the electrons very close to the Fermi surface in occupied states or within the Fermi surface can actually get excited to right above the Fermi surface and leaving behind a hole of their original states, and such electron hole pairs, and we call them quasi-particles. And because we know very well that the occupation for free electrons within the Fermi surface is actually 1. Occupation is 1, and out of the Fermi surface, zero temperature is actually 0, and therefore at small but finite temperatures, we can really count how many quasi-particles there, and therefore the momentum space is the natural eigenbasis that we could express this operator. And we try to represent the V operator in terms of the states or operators in K space. So now let's just do this. So if I represent the two initial and two final states as two electrons, in say momentum states gamma and delta, and after scattering, so I create two new electrons carrying different momentum variables alpha and beta, and I could calculate such a meshes element. So V alpha, beta, gamma, delta is nothing but the initial and final states. So initially, we have one particle, one electron in states gamma and delta, and no electrons in states alpha and beta. But finally, we have one electron in states alpha and one electron in state beta, but no electron in gamma and delta state, right? And this is the matrix element of this V operator sandwiched in between the initial and final states in occupation number basis, right? So now we could plug in our favorite eigenbasis, alpha, beta, gamma, delta being the momentous eigenbasis, K, and I can relabel this alpha, beta, gamma, delta in terms of the momentum variables, and that's it. So this is K, K prime, K double prime, K triple prime, K. Okay, suppose it's alpha, beta, gamma, delta are just momentum states labeled by K, K prime, K double prime, K triple prime. Then this matrix element V alpha, beta, gamma, delta is nothing but V, K, K prime, K double prime, K triple prime. So I write it here, this matrix element, either way. Okay, so you could label whatever you like as long as these indices are consistent. Great. So let's try to calculate this matrix element. Okay. Suppose it's alpha, beta, gamma, delta, just single electron, say free electron states with momentum such a value. So so let's look at this. And this is nothing but a Fourier integral because we consider almost free electron. And they are interacting by Coulomb. So these free electrons have a wave function like plane wave as their Schrödinger wave function. Okay, so then we could consider this as a plane wave electron, and therefore the matrix element is nothing but the Fourier coefficient R1, dr1, dr2. So this Fourier component of the matrix element V, K, K prime, K double prime, K triple prime is actually the integral, the Fourier integral of this, where this V R1 minus R2 is the real space potential for Coulomb interactions. Okay, so you take this real space Coulomb interaction as a function of the distance between two electrons. So the Coulomb interaction is actually proportional to the distance between these two electrons, right? And suppose that these electrons are simply just plane wave, like a quantum particle, and you could very easily write down this kind of Fourier transformations between the real space Coulomb interaction and the momentum space matrix element. And this is further decomposed in terms of a Fourier series of this real space Coulomb potential, right? So this real space Coulomb potential term, as a function of R1 minus R2, could be re-expressed in terms of the Fourier component in momentum space V of Q multiplied by this Fourier coefficient e to the iq dot R1 minus R2, but this exponential factors appearing on the left and right part of the V R1 minus R2 are nothing but plane wave function for initial and final states. So this is the final state, and this is initial state. So initially, we have two electrons, say, carrying momentum K double prime, K triple prime, and they are destroyed, and then later, their new two electrons are created carrying a momentum K and K prime. Okay? And the matrix element of such processes is given by this, which is a Fourier integral of the plane wave electrons. But this potential in real space between two electrons could be further decomposed in terms of a momentum space representation of the Coulomb potential. Okay, so any function could be decomposed in terms of the Fourier series, and this is one of them. Okay, so any arbitrary function in real space is expressed in terms of the Fourier decomposition, and this is the Fourier decomposition of the real space potential in terms of the momentum representation of the Coulomb potential, and multiplied by this Fourier coefficient. And now we could just combine this, various exponential factors, and we could carry out this matrix element of this V, K, K prime, K double prime, K triple prime. So let's take a short break. When we come back, we'll finish this matrix element calculation. Okay, so let's continue. So we calculate the matrix element of the Coulomb potential operator in K space, and it involves this plane wave, coefficients in the integral of dr1 and dr2, and also we could Fourier decompose this real space potential term in terms of the Fourier component of the potential, which is VQ times this e to the iq dot r, r1 or r2. So then we sum over, or we integrate over this entire dr1, dr2 real space. And when we perform such a double integral, and we know that there's a Dirac delta function emerges, because this e to the I k dot r dr is actually delta function. And this delta function, this Kronecker delta function, right? So which is non-zero. Of course, we need to divide this by a volume vector. Okay, so now we obtain this Kronecker delta function, okay? And there's two delta functions here. So one's for the dr1 integral, another is for dr2 integral. And these two delta functions need to be multiplied with each other, and we sum over momentum q. And this is our matrix element, right? So just two delta functions in the product form, and you sum over q and multiply by v of q. So now we could just plug in this matrix element back to this operator form of a Coulomb potential in moment and space, and this is it. And of course we have two delta functions, right? Good. So, but the summation is over all momentum variables, including q and the four momentum k, k prime, k double prime, k triple prime, sum over q. So we can get rid of two of these five summations, right? So say let's just get rid of this double prime and triple prime. So we could just plug in the condition is that this Kronecker delta function gives you 1, which means that this argument inside the bracket vanishes, and this also vanishes, which means that k double prime is actually k minus q, and k triple prime is actually k prime plus q, right? So you plug in this condition, which makes this Kronecker delta function being 1, and get rid of this k double prime, k triple prime summation. And when you have done this, you get just a triple summation over k prime and q. And these momentum indices carried by these operators, are changed to just the k and k prime and q variables. And we, plug in these relations into the momentum indices of these operators. And this is the final expression for the Coulomb interaction in second quantized form, but in momentum space. Okay, so you could use a graph or a diagram to understand such scattering processes in momentum space, Coulomb interactions in K space, in the following form that there are two electrons carrying momentum k and k prime, and when they interact by Coulomb, these initial two states are destroyed, and then after scattering, there are two electrons come out carrying momentum k plus q and k prime minus q, where this momentum q represents so-called momentum transfer. Okay, so the momentum transfer is a very important concept in the scattering. So these two electrons actually exchange, or their momentum with the, say, this wavy line. So this wavy line represents this Coulomb interactions, but in the second quantized form of a Coulomb potential or scattering, and this wavy line represents the photon gamma. Okay, so in other words, the Coulomb interaction, okay, is nothing but, in the second quantized language, electromagnetic wave. Electromagnetic wave is nothing but photon. Okay, so in the second quantized form, you could consider this wavy line as photon. Okay, so the photon mediates, say, the Coulomb potential in between two initial and final electron states. And the photon carry momentum q, and the direction of the photon propagator is upwards, right? Positive z directions. So therefore, you get two interaction vertices. One is the bottom, where this initial electron state k prime, when it interacts with the photon, it loses the momentum q, and its final state electrons associated with k prime becomes k prime minus q, as a momentum states. And the initial states carrying momentum k, when it absorbs this extra momentum carried by photon at the final state, this electron carry k plus q. Okay, so there is one electron carrying q momentum less, and another electron carry additional momentum q. So the momentum is always conserved right here at the bottom vortex, and also top in the intersection between this photon and these two electrons. So you can see this momentum conservation right here as the initial momentum k. It's actually get destroyed, where this momentum is actually pointing to that intersection, and it actually absorbs a photon carrying momentum q, and therefore when k actually meet with q with the same directions, and this momentum is actually added up, and therefore it is the same as the final state electron, where this photon is destroyed, right? So you could consider this as electron photon scattering, where these two electrons come in, but there is a photon actually created right at this bottom spot, and then it's propagates along that direction, and then it is absorbed by these incoming electrons carrying momentum k, and after absorption of this photon, this momentum got absorbed by the final state electron, and the photon is gone. Okay, so this is the point of view from the electron photon scattering, but in fact it is the same scattering as a Coulomb scattering between two electrons, but we should consider these processes in the second quantized language. Okay, so the second quantization of the Coulomb interaction will be discussed later. So we could second quantize this Coulomb potential in terms of the photon creation and destruction operator, where photon is a boson. Okay, so at this point, you don't need to understand this relation between this photon and the Coulomb interaction, but you need to understand that at each of these two intersection points, or vortex points, the momentum should be conserved. Okay, and therefore, if you look at this momentum conservation at the bottom point here, so initially we have electron carrying momentum k prime, but somehow this momentum is distributed part of this by this photon. So the photon actually eats up part of this momentum q. So after this emission of this photon, this momentum, the remaining momentum is actually k prime minus q. So, and that's what you should consider and think of when you think about this Coulomb scattering. Using this momentum variables, it is much easier to understand what is going on here, because we know for almost free electron gas, and we could count the particle number by counting how many electron hole pairs near the Fermi surface. Okay, and therefore, this momentum eigenbasis is always a better starting point to understand the electron Coulomb scattering. So instead of using the real space destruction and creation operator or real space Coulomb potential, we should start to consider the K-space version of the Coulomb potential. And this is the momentum space version of the Coulomb interactions. And I think this is much more relevant for the solid state, because for metals at low temperatures, and this is precisely what happens. Okay, so there's some electron hole pairs created, and then electrons can interact with other electrons near the Fermi surface with precisely this kind of processes. So now let's look at what this value is, this V of Q. Right here is just a Fourier component of the real space Coulomb potential, 1 over R potential. And we know very well this Coulomb potential is 1 over R, but what is V of Q? Right? So this is what we need to carry out. So the V of Q is nothing but the Fourier component of V of R. So if I use this to simplify the notation, this small r represents the distance between these two electrons, and this V of Q is nothing but this Fourier integral. Okay, so E squared over R e to the minus IQ dot R, and integral over entire real space. So let's do the integral, and you will find that this naive, innocent-looking integral is really troublesome. Okay, so it gives you infinity or not convergent results when Q is very, very small. So let's do the integral. Minus IQ dot R. Remember, this is a three-dimensional integral, so dr carries a vector, right, in three-dimensional space. So you could use your favorite spherical polar coordinate to rewrite this in terms of integral over the cosine theta and the integral over the radius part of the coordinate. This is your spherical coordinate, and because its Coulomb potential shows a spherical symmetry, right? So because it depends only on the distance between these two electrons, and if this distance is the same, you get the same potential energy, and it doesn't matter the orientation of this two electrons as long as they have the same distance. Okay, so this spherical symmetry of this Coulomb potential allows us to use the spherical coordinate, to carry out this calculation. But the non-trivial factor is this e to the minus IQ dot R, because Q is arbitrary, it's a momentum transfer wave vector, which can point to any direction in three-dimensional space. But you can always calculate the angle between this Q and R. And the angle is this theta, right? Okay, suppose this is Q, suppose this is R. The angle between Q and R is just a polar angle. Okay, so, but of course there is another angle in the xy plane. It is called azimuthal angle, phi, but this phi doesn't appear in this integral, so you can integrate over this entire azimuthal angle from 0 to 2 pi. Okay, so you get just factor of 2 pi. So coming from this integration over d phi. And Q dot R is nothing but the magnitude of Q times magnitude of R times cosine theta. And the only angle that you need to integrate over is the theta. And theta, in this polar coordinate, you get sine theta, right? The theta times 2 pi, right? So you could rewrite this as d cosine theta And the range of this cosine theta is from, say, 0 to pi or pi to 0. So this is 2 pi e squared, 0 to infinity, the r, 1 over e to the minus I q r cosine theta, and there's the theta, d cosine theta, minus 1 to plus 1. Okay? So theta ranges from 0 to pi, which means that cosine theta ranges from plus 1 to minus 1, minus 1 plus 1. But there's a minus sign here. If you change the variables from d theta to d cosine theta, and therefore you simply just reverse the upper and lower limit of d cosine theta to minus 1 to plus 1. Good. So if I call this, say, cosine theta x, then I can rewrite this integral e to the minus I q r x and dx minus 1 plus 1 dx. It's called solid angle d omega. Okay, so let's erase the blackboard. When we come back, we'll finish this, another half of this calculation. So you'll see that it's not that simple calculation. It has tricks. So before we ended over there, just a minute ago, this v of q is given by these two integrals, the r and the cosine theta or the x. So we could integrate over the x, the cosine theta, very easily. And after we get rid of this the x integral, you get this form where this e to the minus I q r x, taking the difference between the upper bound and lower bound. Okay, minus 1 to 1. And you plug in this, two values, minus 1 and plus 1 of x, and you subtract one from another, and you get this form. And this naive looking form is actually not convergent. Okay, because in the bracket we have this e to the minus I q r minus e to the plus I q r. What this is? Well, this is proportion to the sine function, right? And you know very well from your applied maths that if I integrate over this entire real space with a sinusoidal or oscillatory function like sine or cosine, which is kind of oscillate, right? In real space. But you know that this range of integration goes from 0 to infinity. Okay, so you get many cancellations, but of course, when r goes to infinity, and you cannot just cancel all this plus sign minus sign of this integrand. Okay, so in the finite q, but very long distance, r goes to infinity, and this in this very long range limit, and you get infinity. Okay, so this is infinity. Okay, so you could try to plug in this in your computer, and you will see that this integral does not converge. It sounds strange, very strange, because the Coulomb interaction is certainly a finite value function, okay, in real space. But how can this Fourier components v of q diverges? So what does that mean? So no matter what this means, we need to fix this. At least mathematically, we need to make this value a finite one, a finite value, artificially. But we know that it doesn't help. In the long term, it's just temporarily fix this divergent behavior. So is that we introduced a decay factor e to the minus delta times r, where delta is very small, approaching 0. In this 0 delta limit, we calculate this stuff, and the advantage of this decay factor introduced here is to guarantee that this long-range Coulomb force is cut off. Because when r goes to infinity, if delta is positive and small, no matter how small this delta is, this infinity of this r is going to introduce a cutoff because this is a exponential decay. Okay, so this exponential decay, is going to cut off the Coulomb potential in the long distance limit, and therefore, artificially this will not diverge. Okay, but it's just a temporary fix because delta approaches zero eventually. But we don't send the delta equals zero first, but we just make this delta a very, very tiny parameter here, but to guarantee that this Coulomb potential is cut off. And then we take the limit of delta goes zero later. Okay, so this is a trick that we could temporarily fix this divergent or not convergent integral. But let's just pretend that we can fix this problem. Okay, so let's just put this convergent factor here to guarantee that this Coulomb potential is convergent when you perform such a integration over r, and therefore we get plus I delta of r minus e to the minus I q minus I delta dot r, right, times r. So in other words, we put this extra factor e to the minus delta times r, which is I times delta times r, right? I times I is minus 1. But here, with e to the minus I q r, we should insert minus I in the bracket to guarantee that this is also a decay factor. Minus I times minus I is minus 1. So then this is just artificial factor that we put in by hand, and just to make us feel better for now. Okay? So then we could just carry out this integral, and it is given by this. If you integrate over the r of this factor and that factor, you subtract one from another, and you get to additive result, which is I over q and 2 times I over q. And this IQ is always here in the denominator, so you cancel this I. You get what? You get q squared 4 pi e squared. It looks good, but of course there's a little delta here. So what does this give us? Well, this may give us just a small delta square in the denominator, but in the limit of delta goes 0, this goes away. So you could just approximately consider this v of q as just 1 over q squared. But still, this long-range nature of a Coulomb interaction is still there, because we will see that when q goes 0, in the limit of q goes 0, you get infinity. You still get infinity. What does that mean? So it means that this q goes 0 limit of v of q is what? E to the I q r dr. Suppose I have this kind of Fourier relation between v of r and v of q. But what is q goes 0 limit of v of q? Well, when q goes 0, then this exponential factor just goes away, right? So when q goes 0, this e to the I q dot r is actually e to the I 0 dot r, which is e to the 0. E to the 0 power is 1, right? So what does it mean? So this means that, in the q goes 0 limits of v of q, it simply means that you sum over all potential energy over the entire space, which means that it is the average potential over space. So you take the average value of your Coulomb potential over entire space by evaluating this dr integral of v of r. Meaning you just calculate what is the value of this V if you sum over all contributions from all different R. Okay, so this is something like, you know, V of R1 and V of R2 and V of Rn and whatever V of R prime. Okay, so you simply just sum over all possible R in real space of a V of R. Okay, so this is nothing but the average potential energy, Coulomb potential in space. But we know that, you know, in order to calculate this thing, you need to count how many pairs that you have, right? So we know that there are almost infinite number of electrons and ions, but if we just count the electron pairs, and you still have almost infinite number of electron pairs, right? N times n minus 1, that kind of electron pairs. So, which means that, you know, this number simply just count how many electron pairs in your system. And we know that this number of electron pairs, or in this realistic solid state system, is actually infinity. But how come that any physical quantities could be infinity? Could this be measured? Can we measure this number of electrons to be infinity in any realistic solid state material? Of course, we cannot simply just count the number of electron pairs in the realistic materials, but don't worry. So this infinity is just not artificial, but it will be cancelled by so-called charge neutrality condition. Meaning, in a realistic solid state material, remember, in addition to electrons, there are ions, right? Okay, so this quantity that Q goes zero limit is nothing but the proportional number of electrons in your system. Okay, it's not the full story because it only counts the number of electrons, but we have also ions, right? So the Coulomb potential in the realistic systems consists not only the electron-electron interactions, but also ion-ion repulsion and also electron-ion attraction, right? So we'll see next lectures that this infinity that we encounter here seems like a trouble, but it's just part of the story because this is just counting the number of electron pairs, but it doesn't know this ion pairs and also electron ion pairs. But we could use similar calculations to estimate the V of Q when Q goes zero, but for ion-ions and also for electron-ion. Remember, electron-ion potential is actually attractive, right? So we got 2 positive infinity minus 1 positive infinity. So we got infinity plus infinity minus 2 times infinity, which is 0. Okay, so in other words, we'll see that next time, right? So this value here is proportional to the number of electron pairs, but the other 2 terms are also proportional to the number of ion pairs and also number of electron-ion pairs. But since this whole system is charge neutral, because there is no extra charge in this metal or ordinary solid state materials, so the charge must be neutral, meaning that the positive charge ions must be cancelled by the negative electron charge as a total charge. So the total charge is actually 0 because all this positive ion charge are cancelled by the negative negative electron charge. Okay, so even though we just look at this electron-electron interaction, we know that there is infinite number of electron pairs, but don't worry because there are still infinite number of ion pairs, but there are twice as many as electron-ion pair that leads to this attraction. Okay, so you got 2 infinity minus 2 infinity, which is 0. And this 0 is guaranteed by the charge neutrality condition of a solid state, because the total charge is 0, and this summation over this, plus infinity and minus 2 infinity is just reflecting the number of charges in your system. The number of charges in your system, the total charge system is 0, and which implies that this, after you sum over all pairs of particles, electron, electron, ion, ion, electron, ion, you must cancel out, because the system doesn't have extra charge. So this charge neutrality condition guaranteed that this infinity will go away, and therefore we simply neglected this infinity here because of the charge neutrality. And next time we will finish this argument, and then we will estimate the average kinetic energy and potential energy of a nearly free electron gas, okay, in metals. And this is the first thing that we calculate based on this second quantized formulation. Okay, so please read the corresponding chapters and sections in Flansburgh and also in Kittel's second book, and then you review your quantum mechanics, especially the Dirac representation of the quantum states.